Oh, okay. I guess so. Hello, I'm Lāse. I am a master's student at the Institute at the University of Latvia, and I work at the Institute of Atomic Physics and Spectroscopy. And I will tell you about the liquid Līstra-Galvī mode humidity sensor that we have developed here and its applications. So you already just heard from my colleague what are Līstra-Galvī modes, so I won't repeat that. But specifically about our resonator, we have chosen a liquid, a viscous liquid, glycerol, as the resonator. And we chose it because it's very hygroscopic, and so when air humidity changes, then glycerol absorbs or lets back in the air moisture, and therefore the radius and refractive index of the droplet change. So this causes the change in a resonant wavelength, and we can detect this change. This is the experimental setup in our laboratory that we have created at the moment. Here in the scheme, you can see that inside the climate chamber, there's a glycerol droplet that we can change the position of, and we use a 760 nanometer tunable laser with which we excite the VGMs, and we detect the signal and then read it with an oscilloscope. And yeah, quickly you can also see how it looks when the droplet has been excited. It's around 250 microns in radius. And we have also developed a data analysis method that is quite original for this kind of sensors. So this is what you see in an oscilloscope screen in time, how the modes are shifting in screen. And at these 2 points on the red curve, x1 and x2, we collect data in time, and that creates these two sine graphs that have a phase difference of around 90 degrees. And from those, we can create a Lāse figure. That allows us to see if the humidity is increasing or decreasing, because depending on that, Lāse figure is being created in time or clockwise or counterclockwise. And the angle shift here represents the wavelength shift, as one full circle corresponds to free spectral range of the modes. So we have achieved very high sensitivity and also repeatability. As you can see here in the graph, then with 15-day difference, the measurement stayed the same with almost no change, and also the sensitivity of this curve is very high. It's 2.85 nanometers per percent relative humidity, and that is like around 1 order higher than any other mentioned in publications. We also measured the temperature dependence, as it is a very important parameter, and we concluded that when there are small temperature fluctuations, such as for up to around 3 degrees Celsius, then there is no additional wavelength shift. When the temperature changes more, then we also start to notice some difference here between these two curves, when the temperature was constant and when the temperature was increased. But small temperature changes don't influence our results, so that's very good. Then, based on these properties, we also indicated the areas in which the glycerol droplet sensor could be applied. And one of those, especially that we are thinking about, is pharmaceuticals and chemistry, as they're for making different drugs, it is necessary to have specific air humidity, and otherwise it can influence the structure of different pills, and it can create bacterial growth and other undesired effects. And there are also other areas. Yeah, so glycerol has a very low temperature dependency, as it was seen. So it's when compared to many of the solid resonators, it's a very big difference from those. It has a long lifetime, and another interesting effect is that the dust that is in the air, when it lands on the droplet, it doesn't stay on the surface. It goes into the volume of the droplet, and therefore it does not ruin our resonators. It could happen anyway, that there's so much dust that it becomes a problem, but a little of dust does not influence. And yeah, so one of the highest sensitivity demonstrated, as it is a very hygroscopic liquid. Also, we have started to measure the selectivity of our droplet, and its first results seem to be pretty nice, because the droplet doesn't feel ethanol and other similar substances that could be in the air of labs and hospitals. We are also using a low power laser, and that creates extra safety. And glycerol itself is non-toxic, it's accessible and very cheap material. Additional conclusions that one of the, like there's the dust problem a little bit, but a bigger problem are the vibrations, like everyone in, with our sensors. So we have to limit the vibrations or think about creating a smaller droplet, as that reduces the impact of vibration. Yeah, we want to continue working on measuring selectivity and making our setup smaller. And if you want to read more about our experiments, then you can check out this article that we recently published. Thank you.
Thank you, Lāse. Some questions, please. So I don't see questions. I would like to comment that yeah, we have found a small niche with this glycerol droplet, and yeah, it is possible to excite whispering gallery modes not only in solid resonators but also in liquid resonators. So yeah, good luck, Lāse.